Bismillahirrahmanirrahim. Good evening, everyone. Today we will try to do a summary to this article. This article's name is Direct Observation of Current-Induced Conductive Path in Colossal Electroresistance Manganite Thin Films. I will focus on these simple things: abstract introduction, experimental details, summary, and at the last, the summary and the resource. We will work on this constructor, the simple letters to attract this structure is LPCMO, lithium, barium, calcium, manganite, oxygen, perovskite, manganites, depending on what. We will discuss all of that. And the current can lead us to what? The last will be the relation between the current and the resistance. We will explain all of that by using some images to make these important ideas be clearer to us, and we can understand all of that by using all of them important images. For perovskite manganites, we have physical properties dependent on simple things in perovskite manganites. These physical properties is dependent on magnetic field, electric field, strain, pressure, light, and current. At the last, we can say the current reshape the ferromagnetic microscope domains without changing their actual volume fraction. The current can assist percolation of the ferromagnetic microscopic domains to form conducting pathways. We will take more information about this domains and what's the shape, how we can note the exchange, the change in these domains, and how we will say the bridge between us by increasing what and when. The current can lead to what? The current can lead to increase the magnetization and at the same time decrease the resistance, like this constant system, this our constructor was observed, which has been understood as current-induced transition from isolating charge order to ferromagnetic microscopic state. Note here the relation between the spin and charge are strongly coupled in manganite system. The spin and charge has strong relation between them in the manganite system. The current lead to anisotropic, some different transport behavior in this structure system, which is indirectly supports the Dielecke-Curves's model. By using a magnetic forces microscopic, or we can say it's easily MFM, that's mean magnetic forces microscopic, that the current doesn't change the shape of the ferromagnetic domains. The current doesn't has any relation with the shape of ferromagnetic microscopic, and no way to can change the shape or characteristics of this ferromagnetic microscopic domains. But a few small ferromagnetic microscopic domains appear at critical regions to bridge large neighboring ferromagnetic domains. I will explain all of that by using the image at the next slides. Now here, it's very clear image to us to explain to us this behavior. Here, at this cycle, or this spherical, we note some points, but some distance between them. Here, we can say the distance is smaller than, and this picture can illustrate to us this phenomena better. Here, by increasing the current, here when we dealing with zero current, this distance between these 3 points is clear. When increasing the current, this distance start to disappear. After that, by increasing the current to equal 30,000 angstrom divided on centimeter square, we can say this distance between them is disappear totally and something like bridge. Magnetic ferromicroscopic is usually used for high resolution magnetic image. Usually we use this magnetic ferromicroscopic in two situations. Usually the first one, high resolution magnetic imaging and detecting for molecular interactions, the interaction between these molecular. And we have some advantage about this MFM, magnetic ferromicroscopic, from the AFM, atomic ferromicroscopic. Lower noise and higher resolution. Here it's something like, no, the tiny addition of ferromagnetic microscopic domains doesn't lead to a noticeable increasing in the global magnetization measurement. Here, the important slide started from here at figure 1. We will dealing with the temperature at the x-axis by Kelvin unit and the resistivity ohm centimeter at the y-axis. And we will apply different amounts of current, start from 2 angstrom divided on centimeter square until 2 dots, or we can say 20,000 angstrom divided on centimeter square. But here's some difference. Just the last one will be plus amount, plus charge, but the others are continuous. Here, by using different colors, started from the black one, started from here, from the room temperature, and until this point acts to us the transition temperature, isolating metallic transition temperature, and equal to us something like approximately 1,000 ohm centimeter. When increasing the current, we will note the resistivity will decrease. That's clear. Here, for example, at the yellow one, 2,000 angstrom centimeter square divided on will equal approximately less than 1,000, less than 100, sorry, more than 10, less than 100 between them, decreasing from 1,000 to less than 100. It's exponential decreasing, huge decreasing. And at the same time, the transition temperature is decreasing. Here, it's more than 100 Kelvin. Now, let's take a look about this information. As figure A shows the temperature dependent resistivity of the sample of this compound, film at different measuring I density. Like I said before, we have 6 different amounts of current density by 4 orders of manganite leads to increasing the temperature, transition temperature, isolating metallic, and 80 Kelvin here, 80 Kelvin. the bigger resistance value here at 80 Kelvin. 3 orders of manganite drop, decreasing of resistivity below transition temperature. The resistance temperature curve measured and continuous current with the same I density are nearly identical. Here we can say these curves will be identical from 300 to more than 200 Kelvin, will be something like that. And after that, at less 50 Kelvin will be something like that. Between these 2 points, we will note something like hysteresis phenomena, because when we cold this this compound, can't say it's more appropriate, when cold this compound, we will it will take away, and after that, when we warm the same compound to the same 300 Kelvin at room temperature, we will say this compound will not take the same path. Here are these 3 critical temperature, 150, 80, and 10, with different amount of current density, as shown in all 3 cases. The sample was closed from room temperature from here, cooling the compound from here, warming, to the measuring T temperature under 0 current, milliampere period to measurement. The most important things this in this slide is the image. We have 3 critical points act to us some different behavior, and between these 2 points, the hysteresis phenomena to all of these compounds, and this critical point, critical temperature 150 and 10, these or more than 10, this hysteresis phenomena will disappear to all of these different current densities. At 10 Kelvin, the resistivity after current circle remains 3, or the some ratio between these few colors, between these few different amount of current density of manganite magnitude lower than that before that current cycle, indicating an irreversible change of the transport state in the film. Resistivity measured in the perpendicular direction drops by less than 1 order of magnitude in the same I current. I will focus on the image because it's the more important things in this presentation. Here at high temperature, at 150 Kelvin, the change of the resistivity become almost recovers the original value after the current cycle at this point. And after that, we can say the hysteresis phenomenon will start at all of these different colors. Here we calling the compound from 300 Kelvin goes to 0 Kelvin. Here we have, we will talk about the ratio, the induced resistivity change current at 10 Kelvin. The resistivity here equal to 126,800, 100%. Actually, it's a huge amount. It's a huge ratio. And this image illustrates to us for at 10 Kelvin. Here, when we increase the current density from 3 goes to 0, and after that, increasing in from 0 goes to 3. Sure, here too we will say some approximately, or we can say some the same hysteresis phenomena, because when we in decreasing it and increasing it, we will say the compound will follow different path. At the same time here, it goes to -3 and come from, when we will come from -3 goes to zero, some similarity about the Hertz's phenomena, but here it's less than the right side. At 80 Kelvin, some similarity and at the same time some difference about the amount, because here this line is more increasing than the first one, but the same idea, decreasing the current resistivity and increasing the current resistivity. We will say some different paths. We will note two different paths. And here, when decreasing, the current density goes to -3, and when we'll come from -3 to 0 again, it's smaller than we have, but smaller than the right side and smaller than the first one. And here the ratio equal 26,100%. And at the last one, this image will act differently from all these two images before. The resistivity equal 4,300%, and the line at above the zero is disappeared, totally disappeared. And when increasing and decreasing the current from these two, both of these two sides, we can say both of them it will take the same path without any hysteresis phenomena again. And the line above the zero will disappear totally. To its causal effect on a train, the current appears to have a little influence. The current has a little influence on the magnetic properties of this compound. For this compound system, no change of the initial magnetization. We don't have any change about initial magnetization at the sample. Curve clearly indicates that the total volume fraction of the ferromagnetic microscopic phase is not affected by the current. The same current density induced more than three orders of magnitude drop of resistivity and 80 Kelvin increases of temperature resistance, transition temperature, isolating metallic. Here we have two important notes. The current cases a large change of conductivity without increasing the volume fraction. The current cases, because the current large change of the conductivity will increase, like I said before, with increasing the volume fraction of the ferromagnetic microscopic. By that, the current reshapes the ferromagnetic domains to become elongated along the current direction, makes the percolation easier to this ferromagnetic microscopic, and current doesn't change the shape of the domains, but instead causes some teeny ferromagnetic microscopic domains to appear at certain critical regions, like I explained at the previous slide, region along the conductive pathways. Here, both scanners can result in large change conductivity, little change of total magnetization. The conductivity will be increased with little change in the magnetization. Here, this figure illustrates to us the different nanometer to the compounds and explain to us what that means, the dark ways and the bright ways between them. The dark ways, the bright area explain to us the negative phase, the dark area, the dark phase explain to us the positive area. Here, the positive area are the bright region explain to us the negative area. And between them, approximately some similarity chains above and below. Here at 10 Kelvin, magnetic ferro microscopic image at 80 Kelvin at these two different temperatures shown on supplementary material. And the magnetic ferro microscopic image, dark area, like I said before, negative phase, bright area, positive phase, represent ferromagnetic microscopic and isolating charge order phases. Here, we came back to this image again. We used it when we want to start to explain the bridge between these few atoms or columns, shows magnetic ferro microscopic image occurred at 10 Kelvin after zero current cooling process. A series of magnetic ferro microscopic image are obtained after current cycles with different maximum current density. Here it's not very important. The previous image, it was more important. Here, take another look to this bridge, to this atoms, and when increasing the current density, how these few atoms, diamonds, start to convert to make something like bridge, with disappear all the distance between them to be something like one bridge. I explained that before. After the current cycles, a few small ferromagnetic microscopic domains appear to bridge. Except the current induced ferromagnetic microscopic bridges are more difficult to be observed by magnetic ferromicroscopic, which is likely caused by the fact that the magnetization at 80 Kelvin is weaker than 10 Kelvin. Why? This reason related with the current induced ferromagnetic microscopic bridges are more difficult to observe at magnetic ferromicroscopic, which is likely caused by the fact that the magnetization at 80 Kelvin is weaker than 10 Kelvin. Finally, we have another compounds, another simple RN is a resistor network model exactly based on the magnetic ferromicroscopic results to show that the appearance of a few ferromagnetic microscopic bridges can result in bigger than 3 orders of magnitude change of resistivity, 3 orders bigger than. The conductivity ratio between the ferromagnetic microscopic and isolating charge ordering phase is estimated to be 100,000 at 2 critical temperatures. These 2 critical temperatures are 1 to 10 Kelvin. Now let's take a look about what is the network model. A network model is a database model that is designed as a flexible approach to representing objects and their relationships. And we can say is a unique feature of the network model is its schema, which is viewed as a graph where relationship types are